Okay, so now we're going to do this other example. By examining the cases n equals 1, 2, 3, and 4, making conjecture about the sum. Okay, so for n equals 1, we're only going to add the first one, we get a 1. For n equals 2, we're going to add the first two, and so we go 1 plus 4, which gives us a 5. For n equals 3, we're going to add the first 3, 12, 13, 14, 15, 16, 17. And for the last one, n equals 4, we're going to do 32 plus 12 plus 4 plus 1. And so we get 44, 45, 46, 47, 48, 49. Okay. Now, if we're looking at how this is growing, we need to compare it back to n. So for n equals 1, we just have our n value. So that's probably not the formula that we want to do. But if we start playing around with things that kind of look like what we started with, so we want to kind of look at things like this. So let's try something just like 2 to the n and see how close we get. So if we do 2 to the 1, that for n equals 1, 2 to the 1 is going to equal 2. Okay, that didn't work out. So to force that to be true, I'm going to have to say 2 to the n minus 1. Okay, if I do that, I get 2 to the n minus 1, or when I plug that in, I get 2 to the 0, and that works. Now, if I try that over here though, I'm going to do 2 to the 2 minus 1, and that just gives me 2 to the 1, which is 2. That's not 5, so I have to go back to the drawing board. Now, maybe the issue wasn't that I chose the wrong exponent. Maybe I needed to multiply something out in front. So I'm going to play around with 2 to the n, or 2 to the 2, and figure out ways that I can get that to 5. Okay, so I have 2 to the 2, that's going to give me 4, so I need to add 1 to that. Okay, so if I pull that back, that would be 2 to the n plus 1. Now, if I try it on the first one, 2 to the 1 plus 1 gives me 2 plus 1, which is 3. That's not a 1. If I try 2 to the n plus 1, and I plug in n equals 3, that's going to be 8 plus 1, which is 9. So it's not really working out for me. So maybe I need to multiply something out in the front of it. So let's try 2 to the n plus 1 times some number. So I'm just going to call this an x for now. And let's try it again. Let's try it with the 3. So 2 to the 3 plus 1, and then times by some number. So if we do that, we're going to get 8x plus 1, and we want it to equal 17. So if I subtract 1, I get 8x is equal to 16. Divide that by 8, and x equals 2. So if I plug in a 2 here, how do I take that back though? I want to put it in terms of n. Well, n was 3 and 2, so maybe it's n minus 1. Alright, let's try that and see if it works for the first 4 cases. Okay, so try it for 1. So we do 1 minus 1, 2 to the 1 plus 1. That's 0 times 2 plus 1, which equals 1. So that works. Now let's try it for 2. 2 minus 1, 2 to the 2 plus 1. So that's 1 times 4 plus 1. That's 4 plus 1, which is 5. So that worked. We made this equation based on this one, so we know it works. So we're going to skip to 4. 4 minus 1, 2 to the 4 plus 1. 4 minus 1 is 3. 2 to the 4 is 16 plus 1. 32 plus 16. Okay, 48 plus 1 is 49. So this works. So since all 4 of them work, this conjecture is true, at least for those first 4. Once again, we didn't prove this for everything, but we used inductive reasoning to convince ourselves that it could be true. Okay, if you need additional help, come to Math Lab. Until then, calculator.